Okay, so this is Newton's law of gravitation.
Welcome to my world, Kabi.
And it's basically what it says is that force is proportional to the masses of the two objects that are being attracted to each other by gravity, and inversely proportional to the distance. And the constant of proportionality is g. And this is a very small constant. 6.67 times 10 to the negative 11 in case you're wondering, but that'll be provided on the equation sheet. There's a problem on that, but I don't think we should really spend too much time on this. It's pretty simple comparatively to the other stuff we're going to go over. Okay, so now centripetal motion, because this is useful when you're trying to describe the motion of planetary orbits. Now, most of them are actually ellipses, as we'll cover with Kepler, but they can be modeled by circles because they're pretty close. So we've got, it's like this. We've got the radius of the circle.
Darker.
Can you use a marker?
Can you perhaps?
Yeah, try and find a dark marker.
There you go.
Right there.
Okay, so we've got a circle, and which has some radius r, and there's an acceleration towards the center, and that acceleration towards the center is acceleration due to gravity in the case of celestial mechanics, and of course your planet will have a velocity, otherwise it would just fall directly in, and if you're in physics, you know the equation a equals v squared over r. And that's basically, you can find acceleration if you know velocity and radius, or you know what, you can find any of them with any of the other ones. And this is the centripetal acceleration. So then we can find the centripetal force, which is, then m.a.c. by Newton's second law. Newton's second law F equals ma for non-physics people. And that's mv squared over r. So this is a useful equation. Because you can use this combined with the law of gravity to find identities, solve things. Rachel, okay. We'll go over some problems at the end if we have time. Then we have Kepler's laws. So the first of Kepler's laws is that planets travel in an ellipse with the sun is one of the foci, and there's nothing in the other one. So here's your planet, it's going around. So basically, mathematically, what this means is that radius equals p over 1 plus epsilon cosine theta, where theta is the angle between you and the planet, like that. So this is like polar form, if you're familiar with it, if you've taken math analysis. So there's a few interesting properties of this, type of a construction. We have here a few important laws. So as you can see, cosine is between -1 and 1. So your maximum radius will be at p at 1 minus epsilon, and your minimum radius will be at p 1 plus epsilon. So because if you have a small denominator, you'll have a large value. So when it's at its maximum radius, the planet is called is said to be at its aphelion, and it's called and its minimum radius is called perihelion. And obviously, this is not pertinent to the physics test. This is just astronomy. Garrett.
What's epsilon?
Huh?
What's epsilon?
Epsilon is the eccentricity. I'm getting to what these p and epsilon mean.
Thank you.
So they're basically just parameters that have to do with every planet's, velocity around the, or velocity around its, the sun in this case. Then we have the semi-major and semi-minor axes. So by the way, this is R min, and this is R max, as you can see, because it's the closest here and the furthest here from the sun. Now, as you can also see, the distance between the long end of the ellipse, this is called the major axis, is the sum of R min and R max. So the the radius of the ellipse, the maximum radius, would be that arithmetic mean. So we have our major axis, A, equals r min plus r max over 2. Then we have the semi-minor axis, which is this axis here. And that is, you know, B actually, usually. And that is geometric mean. Not going to do the geometry, but it'll work out. R min. Now, again, this is useful because then you can find, you know, the dimensions of your orbit, and also it'll help with other calculations. Let's say if you want to find if orbits intersect. Rachel.
Sorry, what are A and B again?
A is this distance, and B is this distance. So you have your, it's kind of like the distance from the maximum distance the planet is from the median between the two foci, and the minimum distance that the planet is from the median of the two foci. I'm not sure if I'm pronouncing that right. And then of course we have the semi-latus rectum, which is P. So P is the harmonic mean, which means that 1 over P equals 1 over r min plus 1 over r max. And this is this distance here. So it's the distance from the sun to the planet when it's perpendicular to the, when it's perpendicular to the point at which it would be closest or furthest. And as you can see, that's the point at which theta is 90 degrees or 270 degrees, because that makes this term 0, so it's just P. And finally, we have the eccentricity of orbit, epsilon, which equals which is something called the coefficient of variation, r max minus r min over r max plus r min. So this is another useful constant. And by the way, if you don't want to write all this down, this will be, I have a list that will be posting online. So that's Kepler's first law. Actually, this is Kepler's first law. The rest of it is just a variety of constants that have to do with, or a variety of values. Then of course we have Kepler's second law, and that is that the area that is swept out by, let me draw another picture. I guess I can draw this one here. So the area, or foci here. So the area swept out by the planet at any point in its, the imaginary line connecting the planet and the sun, at any point in its orbit, is constant per unit time. So basically, if you're in calculus, it would be dA over dt equals k. So if you manipulate this a little bit, and again the derivation...
You can use delta.
Huh?
You can use delta instead of d.
That would seem right, wouldn't it? Okay. Delta A over delta t. So if we assume that the ellipse is a circle locally, which works out with calculus, then you end up with the area being base times height, right? So that's the radius of that point multiplied by the arc length divided by 2. So the arc length is r theta. Anyway, if you do it all out, you end up with velocity equals 2k over r. So the velocity at any given point, or actually that should be speed, is inversely proportional to the distance from the sun. So what we have then is a formula for being able to find the velocity at various points, just given their distance. So that's the usefulness of Kepler's second law. Basically what it says is that you're going to be going slow here and fast here. And it provides a mathematical way of finding the exact relationship. And Kepler's third law is probably the simplest one, and that is t squared over r cubed equals k. So t is the period of the orbit, so it's like on Earth the period is 1 year, because it takes us a year to go around, and r is 1 astronomical unit, that's the distance between the Earth and the Sun. So basically t squared over r cubed equals k. For the Sun, k is 1 year squared per AU cubed by definition, But you can use this to solve, like, if you know how long the year is on Mars, you can use it to find out how far away it is from the sun. So basically, it's a useful law in that sense. So that's celestial mechanics basics.
Way darker.
Can you not see that?
There you go. See that? That looks beautiful.
Has to show up on camera.
Yes, yeah, show up on camera.
Most of your stuff is good though.
Super.
That's P, that's A.
Wait, so you're just saying
Okay, so,
Wait, A's one, just that. What's that arbitrary?
celestial object?
it's semi major.
Does it the center? Center of the.
That's the center.
Within the
Center.
How can you compare the two?
No, you can compare it to planets that are orbiting the same mass. But you
Uh,
can't compare it to
so-
one A.
Yeah,
Maybe we'll look
that
back.
makes sense. But
Yeah.
I'm just making sure you compare it like it wasn't specific to Earth. It was one to Mars and one to.
It'll all be equal for every planet. K will be equal for the planet.
Yeah, it's Kepler's laws were expressed in terms of the solar system.
So K is equal for Jupiter as it is for Earth.
Yeah.
Yeah.
K? For what? Wait.
Yeah.
Which K? This K?
Yeah.
Yeah. The constant is equal for the body that you're orbiting. So the K for the moon around Earth will be different from the K for the Earth around the sun. But it'll be the same for the... And you'll find that out if you do the last problem.
Are the radius of the orbit the average radius of the orbit, or is the radius of the planet or the body itself?
R? Oh no, the radius of the bodies are we're assuming point masses. R max...
No, not that one.
No. Yeah. We're assuming point masses. The radiuses of the orbit. It doesn't matter if you're Jupiter or if you're like Mercury.
It's the average radius because it's like ellipse.
Yeah.
Right?
It's the I believe it is. John, I think it's A. It's either A or B.
For what?
For this R value.
Oh, it's A. It's A.
It's A. Okay. It's actually A. I should change that.
So it's like so it's the furthest distance.
It's not the furthest.
No, it's the
average of the
yeah, it's
furthest
the average
to the
of the
smallest.
Oh,
it's a long way.
Okay, so question 2 is like a standard physics problem. If you find the mass of the Earth, given that its radius is, whatever, and acceleration at the surface is whatever. So basically what you need to do for that one is that you need to set up your equation, force centripetal equals force due to gravity. And then you can, just plug in G m1, m2 over r squared equals the, m acceleration centripetal. And then you know what your acceleration is. You know what your, and you can just cross out the mass of the person. That's here. And then you've got m2 r squared. You know what g is, it's a constant. You know what ac is, you know what r squared is, so you can just find the mass of the Earth. You're not going to go all the way through it. Then, 3, find the equation for the acceleration at the surface of a planet with density rho. Basically, what you need to do is you just need to plug into, again, this equation. You just need to find m2 in terms of rho and v, because we know that density equals mass over volume. So mass equals density times volume. The real interesting ones come, from problem 5 on. So, 5. Given that Earth's semi-major axis is whatever, and its eccentricity is, this other value, find its maximum and minimum radii from the sun. John, how would you solve this problem?
Oh, you just plug in the R max equations, R min equations they gave us, and cosine is obviously, 0 at both of them. Or is 1 and a negative 1, 1 and negative 1.
Yeah, you use these equations.
Yes, exactly.
And then you can solve a system of equations. So that's basically that problem. 6 should be... Garish, what's 6?
I think it's Achilles' comet.
Why would you say that?
No kidding.
I don't know, could you?
Huh?
You want to explain?
Okay, comets... Huh?
50-50, right?
Well,
Pluto and Earth or something
Pluto, okay, well, the point is that comets have really high eccentricities. Because they are, elliptical orbits. Like, you can tell that they're elliptical, unlike the Earth, which is basically circular.
They melt as you post this, and then they melt.
Yeah, the comets have a really high aphelion and really low perhelion because they come really close to the sun and they go out into the Oort belt, Oort cloud. Okay, and I mean, basically, unless people have questions, that's it.
How about how eccentric are most of the planets' orbits?
Well, that value in 5 is actually accurate, 0.02, and Earth is not that atypical for a planet, unless you count Pluto, but Pluto's not a planet. But it has a much higher eccentricity than the rest of the planets.
If Pluto gets into Neptune's orbit,
Yeah.
So this means that the orbits are nearly circular, right?
Nearly circular, which is why we can
Number
use the centripetal motion equations.
There we go.
look at number 7.
7. Okay, explain the case eccentricity equals 0.
It's completely circular.
Okay, explain why it's completely circular in that case.
There's no deviation from the maximum radius of one side and the minimum radius of the other.
So if we look at this equation, eccentricity is 0, so that term goes away. So we end up with r equals p, which is circle.
I think we probably get questions.
Yeah, I have one question duplicated. That's a misprint. It'll be fixed on the version posted online.
Okay.
So 10 is interesting if you want to. I mean, it's 11 on your paper. It's interesting because it's basically it shows you what k is. I guess we could do that since we have a little extra time.
Okay.
So, I mean, we're assuming circular motion, even though Kepler's third law is about elliptical motion, but as I said, it really doesn't matter. So, what we have here is MAC equals GM1 M2 over R squared. And then we can plug in M1 V squared over R equals G M1 M2 over R squared. And then we can plug in, for velocity, 2 pi R over T. Because, you see, if it's a circle, we're assuming circular, it will go around in 2 pi R, that's the distance, right? 2 pi R, so it's the perimeter, divided by the time it takes, period, T. So then we end up with M1, 2 pi R squared over R equals G M1 M2 over R squared. So we end up with 4 pi squared R over T squared equals G M2 over R squared. And as you can see, that it's T squared over R cubed. A and R are the same if we're talking about a circle. We have 4 pi squared. How did I express it? Was it T on top? Yeah. Okay. 4 pi squared over G M2 equals T squared over R cubed, just by rearranging. So what we can tell from this is that the k value is dependent only on the mass of the object you're orbiting, not the mass of the not anything else. It's just these are all constants. 4 pi and G are all constants. So
T is frequency, right?
Huh?
Is T frequency?
T is a period.
If
it was frequency, it would be in the numerator.
Right. You were wait.
1 over 2 is frequency.
1 over 2 is right. Okay. So basically, I mean, this makes sense because the further away you are, right, the longer it will take you to go around. But it's, the interesting part is the exponents. Okay, so I guess that's it. Actually, I had extra time.
Okay.
All right.
Wait a minute, everyone should sign in somewhere. Sign in.